They begin as innocuous green stalks, rustling in the breeze on wide open fields. Yet sugarcane ultimately shapes entire global economies, fuels political debates, and sweetens nearly every aisle of the grocery store. Step into the billion-dollar realm of mega sugar processing, and you'll discover a ceaseless dance of high-tech machinery, meticulous agronomy, relentless scheduling, and controversies hidden behind the sweet crystals you drop into your coffee. In this journey, we'll explore sugarcane's massive industrial life cycle, how it's planted, nurtured, sliced, crushed, and distilled into raw sugar, then refined into the pristine white grains that feed our collective sweet tooth. The story begins with sugar's dual identity. Globally, about 60% of sugar is derived from cane, a tall perennial grass thriving in tropical and subtropical climates, while the rest comes from sugar beets, root crops that flourish in cooler zones. Did you know that in the United States alone, sugar beets account for 60% of sugar production, while sugarcane covers the remaining 40%? This disparity arises from distinct climate requirements. Sugarcane demands hot, moist conditions in places like Florida, Louisiana, or Hawaii, while sugar beets thrive in temperate latitudes such as Minnesota, North Dakota, and Idaho. Let's focus first on sugarcane, unmasking the high-tech practices that turn vast green fields into a non-stop torrent of raw cane, funneling through giant mills day and night. One typical place to see sugarcane at industrial scale is Queensland, Australia, a region with coastal plains perfectly suited for cane cultivation. Farmers begin by meticulously selecting land with fertile, well-drained soil, ensuring the crop's robust growth. They slice mature cane stalks into short segments, known as sets, each containing at least one node capable of sprouting roots. These sets are planted in furrows carved by GPS-guided tractors, ensuring perfect alignment for the day harvesters come. Rainfall may suffice in some months, but advanced irrigation systems often line the fields, supplemented by modern soil moisture monitoring technology. As soon as sensors detect dryness, automated valves open to drip-feed water. The synergy of technology and nature yields cane that can soar up to 12 or even 15 feet tall within 12 to 24 months. Throughout this growth cycle, the cane's sugar content gradually accumulates in the stalks, stored as sucrose. By analyzing random samples, agronomists determine the optimal harvest time. Too early, and sugar content is subpar. Too late, and the cane risks lodging or increased fiber that complicates milling. These calculations demand real-time data, climate records, soil analyses, leaf color indices from drones, and historical yield trends. The resulting farm management approach is so sophisticated that each acre can receive custom fertilizer blends, right down to micro-variations in the soil. This is not the old guess and hope agriculture. When the cane's sugar content peaks, typically between June and December in Queensland, the harvest begins. Back in earlier decades, farmers commonly set the cane fields ablaze before cutting, a method used to burn off leaves and deter snakes. Today, we see a pivot to green harvesting. Instead of flames, monstrous harvester machines roll through the fields. Their front blades saw each stalk at ground level, rotor blades strip and chop, and a powerful internal fan expels leaves and lighter debris back onto the ground. This layer of leaves serves as mulch, preserving soil moisture and improving fertility. The cut billets, neat segments of cane, are transferred to waiting haul trucks running in parallel to the harvester, ensuring no downtime. The coordination is mesmerizing. Multiple harvesters might operate on a single plantation, each orchestrated by radio calls or digital scheduling systems to keep trucks rotating at maximum efficiency. Remember, cane needs to be milled within a day or it'll begin losing sugar content. For the largest mills, conveyor belts and private rail lines shuttle cane 24 hours a day. Unceasing waves of raw cane flow into the mill's receiving area, where entire truckloads are weighed, documented, and upended onto feeder conveyors. Once inside the sugar mill, the transformation from rigid stalk to sweet crystals accelerates. First, the cane undergoes a thorough cleaning, blasted by high-pressure water jets that flush away soil, pebbles, or stray leaves. Next, heavy-duty shredder drums tear the cane fibers apart, maximizing surface area. Cane emerges as a fine, fibrous pulp known as prepared cane. This pulp heads to a row of gigantic crushing mills, steel rollers applying immense pressure to extract the sugary juice. The leftover shredded fiber is bagasse, a bulky byproduct the mill incinerates in boilers to generate steam. This steam not only powers the mill but may also feed electricity back to the local grid. Meanwhile, the extracted juice is a murky liquid rife with dissolved solids and bits of organic residue. To stabilize it, sulfur dioxide gas is often bubbled through, inhibiting microbial activity. Then, lime powder is mixed in to adjust the pH and encourage impurities to coagulate. This mixture flows into clarifier tanks, each spanning tens of meters, where suspended solids settle and form a sludgy residue. That sludge, rich in minerals, gets repurposed as fertilizer or dried for livestock feed, forming a near-zero waste loop. The clarified juice is next boiled in vacuum evaporators. Under reduced atmospheric pressure, the liquid boils at lower temperatures, preserving sugar quality while rapidly concentrating the juice into a thick syrup. The concentration might climb from around 15% sugar up to 65% or more. Progressing through multiple evaporator stages, the syrup becomes thick enough to drip slowly, honey-like in consistency. Then comes the most critical part, crystallization. In vacuum pans, the syrup is seeded with fine sugar crystals, each no bigger than a grain of sand. The swirling mixture gradually deposits more sugar onto these seed crystals, growing them over time. Workers or sensors carefully watch the pan's temperature, pressure, and Brix, sugar concentration levels, ensuring the crystals develop in uniform size. Once they reach the desired dimension, the mixture, called massicute, moves to high-speed centrifuges. Spinning at thousands of RPM, these centrifuges hurl the mother liquor, molasses, off the crystals, leaving damp sugar behind. The crystals are rinsed with a light water spray or steam to remove additional color. The final raw sugar emerges as a pale golden crystal, around 97 to 99% pure. The leftover molasses might become cattle feed or go to fermentation for ethanol, ensuring minimal waste. If the sugar is destined for direct consumption, it may need a final refining step. At specialized refineries, the sugar is redissolved into a super pure solution, filtered through activated carbon or bone char to remove colorants, and crystallized again. The end result? Pure white sugar. Automated packaging lines deposit 2-kilogram portions into plastic bags, sealed for shipping, or fill industrial sacks for food manufacturers. This modern approach merges centuries-old knowledge with next-gen automation, letting a single facility produce thousands of tons daily with minimal labor overhead. This entire chain underscores the synergy between agricultural complexity and modern engineering. Yet sugarcane's dominance sparks controversies. Environmental groups cite deforestation in places like Brazil's Cerrado or Southeast Asia, replaced by cane fields. Water resources can be overstressed, with some plantations resorting to heavy irrigation in semi-arid zones. Chemical runoff from fertilizer-laden fields can disrupt local rivers or marine ecosystems, especially near coastal areas. Meanwhile, labor practices and working conditions in certain cane-growing regions raise alarms. Some countries still rely on manual harvesters, exposing workers to intense heat, potential injuries, and meager pay. In response, programs like Bon Sucro aim to certify sustainable sugarcane production, covering labor fairness, minimal environmental harm, and decent wages. Mills adopt advanced water recycling systems, capturing and cleaning runoff, or refine bagasse-based electricity generation to slash carbon footprints. Market forces also push transformation. Big beverage and confectionery brands prefer sugar from responsibly managed mills, especially if they want to label their products with eco-friendly badges. Gradually, the sugar industry is modernizing to cope with these demands, though change is not uniform across all regions. But sugarcane is only half the global story. In cooler latitudes, like the American Midwest or parts of France, sugar beets fill the sweet gap. Each year, after a spring planting, neat rows of beets flourish under the moderate sun. By fall, massive beet lifters unearth these conical roots, slicing away the leafy tops. On arriving at the factory, beets are tumbled in rotating washers, removing clumps of mud or stones. Then sharp slicer blades turn them into cossettes, thin curls of beet. These strips go into a diffuser tower, hot water coaxing out the sugar. After a parallel process of clarification, evaporation, and crystallization, you end up with near-identical sugar crystals. The synergy of cane and beets ensures nearly every climate zone can produce sugar in some form, making sugar a truly universal commodity. None of this entirely addresses sugar's broader controversies. Health experts blame rising obesity and metabolic disorders in part on too much added sugar. Governments experiment with sugar taxes to curb consumption, as Mexico and the UK have done for sodas. Meanwhile, consumer demand for sugar-laden items remains robust. The sugar industry weathers these tensions by diversifying. Some mills produce not just food-grade sugar but also refined ethanol for vehicles, a major practice in Brazil where sugarcane-based ethanol is a main automotive fuel. Residual byproducts feed livestock or become organic fertilizers, forging a near-zero waste cycle. Transporting sugar post-production also demands elaborate logistics. Many mills stand near deep-water ports, shipping raw sugar in bulk carriers to overseas refineries. Container ships handle bagged sugar for direct consumption markets. In the case of domestic distribution, large trucking fleets or rail lines carry sugar from mills to major packaging plants or distribution hubs. The cargo's shelf life is quite stable, barring moisture infiltration. But the scale of shipments remains astonishing, with entire cargo vessels carrying tens of thousands of tons of sweet cargo. One lesser-known aspect is the testing and quality control at every step. Cane is tested at weigh stations to measure sugar content, bricks. Factories sample raw juice hourly, ensuring pH and turbidity remain within target. The final crystals might be tested for color index, moisture, grain size distribution, and invert sugar content. Automated labs feed data back to the supervisors, who can tweak clarifier chemicals or adjust vacuum pans. That synergy is quintessential of modern sugar production. Swift, data-based decisions, bridging centuries of stone masonry knowledge from the earliest mills to the present computerized era. Historically, sugar was once so prized it drove colonial expansions, forced labor systems, and global maritime trade. Now, though the moral context differs, sugar remains a huge economic force that influences farmland usage, trade policies, and consumer health. Billions of dollars revolve around these crystals, a commodity bridging every corner of the planet. That is a direct result of how quickly and efficiently sugar can be grown, processed, and shipped by these mega factories running day and night. Even with controversies, there's no denying the mesmerizing scale. Fields stretch to the horizon, harvesters scythe them down, unstoppable conveyors feed the cane into monolithic mills, and steam from bagasse whirls out of towering chimneys. The end product can seem mundane, a bag of sugar. Yet if you hold that bag up to the light, you hold a microcosm of global trade, resource management, and chemistry. The next time you measure sugar for a recipe or open a small packet at a cafe, reflect on the months of growth under a scorching sun, the tandem dance of man and machine, and the labyrinth of engineering that turned raw cane into uniform crystals. It's a sweet marvel many of us rarely pause to consider. As a parting note, sugarcane stands as one of agriculture's most robust crops, capable of multiple regrowth cycles from one planting. Some farms see 5 or more harvests off the same root system before replanting. Meanwhile, researchers crossbreed cane varieties for disease resistance or higher sucrose yield, ensuring future expansions. Beet breeders do likewise for cooler climates, refining seed genetics. The entire sugar world remains in flux. New strains, mechanized solutions, and consumer shifts reshape the industry, while older traditions, like burning cane or manual harvest with machetes, gradually fade. The unstoppable momentum for sugar, though, does not seem likely to abate. Despite calls for reduced sugar intake and the rise of sweetener alternatives, sugar remains embedded in global diets and industrial processes. So that's the broader mosaic. Billions of tons of sugarcane, a global churn of harvesters, trucks, cargo ships, and refineries, culminating in pristine crystals stored in shining silos. This sweet staple we casually enjoy in everyday life is actually the result of an immense network of labor, technology, environmental risk, and historical lineage. From the coastal plains of Queensland to the milling towns of Brazil to cooler regions harvesting beets, sugar's story is simultaneously local and universal, a testament to humankind's capacity to transform nature in pursuit of one simple, sweet taste.